We're going to build on the ideas of limits and continuity by now examining partial derivatives. Partial derivatives are going to measure rates of change specific to one of the two variables our function is defined on. A partial derivative then represents the rate of change in one direction while holding the other variable or variables constant. On a surface z equals f of xy, the partial derivative measures the slope of a cross-section curve. We'll use these as building blocks for tangent planes, gradients, and optimization. To understand the geometry of partial derivatives, imagine a surface and a point on that surface. Then imagine the intersection of the x and y planes through that point and that surface. Those intersections result in curves along the surface like the ones you see in our animation here. The partial derivatives then represent the slopes of the tangent lines along the curves and through the given point. Notice that if we change the x value of our point by moving along the gray curve, only the slope of the gray tangent line changes. Similarly, if we change the y value of our point by moving along the purple curve, only the slope of the purple tangent line changes. Similar to single variable functions, we're going to define partial derivatives in terms of a limit definition. The partial derivative with respect to x for a function f is going to be the limit as h goes to 0 of f of a plus h, comma b, minus f of a, comma b over h. Notice in this definition that the y-coordinate remains fixed. Similarly, we'll define the partial derivative with respect to y, f sub y of a, comma b, as the limit as h goes to 0 of f of a, comma b plus h, minus f of ab, all over h. Again, notice here that for the derivative with respect to y, the x component of the formula remains fixed. So our x partial derivative means we're moving in the x direction and our y is remaining unchanged. The y partial derivative means we're moving in the y direction but keeping x fixed. So that these partial derivatives become ordinary derivatives of one variable slices along our surface. We'll use two different notations to denote partial derivatives. We have subscript notation, f sub x and f sub y. We also have operator notation, which uses a curly looking d over d sub x and d over d sub y. In each of these, the variable that's present tells us that the other variable is being held constant. This geometric idea of moving along one variable while holding the other constant gives us a method for computing partial derivatives. When we want to find f sub x, the partial derivative with respect to x, we're going to differentiate everything with respect to x and treat y as if it were a constant in our formula. Similarly, to find f sub y, we'll differentiate with respect to y, holding x as constant. We'll tidy everything up after we differentiate, and if we're expected to find the partial derivative at a point, our last step will be plugging that point in. Let's try a few examples. We're going to start off with a fairly straightforward polynomial, and we want to find the partial derivative with respect to x, and the partial derivative with respect to y. So the partial derivative with respect to x, which we can also denote with our little curly d. Here, we're going to treat y as if it were a number. So when we take the derivative of 3x squared y, that is just going to be, we're going to take the derivative of x squared with respect to x, which gives us 2x, so we're going to get 6xy. Similarly, when we take the derivative of 4xy cubed, the y cubed gets treated the same way the 4 does as a constant, and we get minus 4y cubed. And then when we take the derivative of 7y with respect to x, because it has no x's in it and we're treating it like a constant, its derivative is 0. Now we'll look at f sub y, the derivative of f, the partial derivative of f with respect to y. Now we're going to treat the x's as if they were constant. So the derivative of 3x squared y is going to be 3x squared. The derivative of 4xy cubed is going to be, taking the derivative of y cubed, we'll bring the 3 down in front, and we get negative 12xy squared. And then taking the derivative of 7y with respect to y, we get plus 7. All right, now we're going to do f of xy equals x times sine of y plus y times cosine of x. And we're going to again find both partial derivatives. So f sub x, or the partial of f with respect to x. In the first term, we have x times sine of y. But since y is being treated as a constant, sine of y is just a constant, so that is just going to be sine of y. In the second, y is a constant times the cosine of x. The derivative of cosine of x is negative sine of x. So we're going to get negative y, that comes along for the ride as a constant, times the sine of x. F sub y, or the partial with respect to y. In the first term, the x is a constant, so now we're going to differentiate sine of y, which is cosine of y, and we're going to multiply that by our constant x, so we get x cosine y. And then in our second term, cosine of x is itself a constant, so we just get the cosine of x. Our next examples may be a little bit more complicated, but we still rely on all of the techniques for finding derivatives that we learned in Calculus 1. So this is a quotient rule problem. The partial derivative of f with respect to x, we're going to square the denominator, and then we're going to do the bottom times the derivative with respect to x of the numerator. So that's going to be 2x. The y squared term goes away because we're treating y as a constant. And then we're going to subtract the top times the derivative of the bottom with respect to x, which is just y. We can expand that out. We get 2x plus 2x squared y minus x squared y minus y cubed all over 1 plus xy squared. And we can combine the two terms that have the x squared y's in them to get a final answer of 2x plus x squared y minus y cubed all over 1 plus xy squared. Now we're going to plug in 0. That is going to be 0 plus 0 minus 0 all over 1 plus 0 squared, which is, of course, 0. Now, because our function looks very similar for y as it did for x, we should expect to see something similar when we do the partial derivative with respect to y. So here, f sub y, we're again going to square the denominator, and then we're going to do the bottom times the derivative of the top with respect to y, which is going to be 2y, minus the top times the derivative of the bottom with respect to y, which is just x. And so we'll get there 2y. I don't know why I squared this up here. That is incorrect. It's just the denominator, not the denominator squared. 2y plus 2xy squared minus x cubed plus xy squared. Nope, minus. All over 1 plus xy squared. And simplifying that, we get 2y plus x squared y minus x cubed all over 1 plus xy squared. And when we evaluate that at the point 0, 0, we see again pretty straightforwardly that we get the value 0. All right, we'll take some partial derivatives now of an exponential function. So our partial derivative of f with respect to x, which of course we know is the same as f sub x. It's an exponential function, which means that inside of its derivative, it always repeats itself. So we're going to get the original function, and then we're going to multiply by the derivative of the exponent. We're using the chain rule here. And we're going to get the derivative of x squared y with respect to x is 2xy, because the y acts as a constant, so it stays in there to multiply. And then the derivative of 3y squared with respect to x is 0, because y is acting like a constant. So we just get that expression e to the x squared y plus 3y squared times 2xy. We'll see fairly similar behavior when we differentiate with respect to with respect to y. So the function is going to repeat itself. And then we're going to multiply by the derivative of the exponent with respect to y. So the derivative of x squared y is x squared, since x is acting like a constant. And the derivative of 3y squared is 6y. And there is our final derivative. For our last example, we're going to do the partials with respect to x and y of a product. So for our partials with respect to x, we're going to take the derivative of the first term with respect to x, so that's going to be 2x plus 0, because the derivative of y squared with respect to x is 0. Y is a constant. And then we're going to multiply that by the second part of our product. Then we're going to repeat the first part of our product and multiply by the derivative of the second part with respect to x. In that case, e to the y is a constant multiplying x, so we get just e to the y. Now, you might want to expand this out. I'm not really sure it does us any good to. It gets sort of messier and maybe slightly more complicated when we do that. And it might be useful to keep it in its factored form for some sort of application. So I'm just going to leave it like that and do the derivative with respect to y, which is going to be, again, we'll take the derivative of the first piece with respect to y, which is 2y, multiply that by the second part of our product. Then we'll repeat the first part, and we'll take the derivative of the second part with respect to y. So the x is acting like a constant, so the x e to the y is going to repeat itself, and we'll get plus 2y. And once again, I'm not convinced the expanded form is any more useful to us, so I'm going to leave it in this factored form. Okay, so we've seen that partial derivatives are going to help us measure change in one variable while we're holding the other constant. So using the limit definition, what we're thinking about here is cross-section slopes. Our computation rules follow the same exact rules we learned when we were back in Calculus 1, with the exception that when we're computing the partial with respect to x, we're going to treat y as if it's a constant, and when we're computing the partial with respect to y, we're going to hold x as if it were a constant. Next up, we're going to take a look at how we might compute partial derivatives for functions of more than two variables. We're going to examine higher order partial derivatives, and then we'll take a look at the chain rule for partial derivatives.